Thanks, Joseph. Appreciate it. All right, my friends. So I found, I can't see my friend Lavina here from back here. No, it's cool. I just couldn't see your head. So I found a Python training that is free. And it's pretty sweet, actually. So honestly, we're going to work on honor system. I would like you to complete this by next Friday. Not this Friday, but the week after. I think it's quite doable. You're going to be getting Python experience, just looking at code. If you are a Python expert and you can just convince me of that through, just give me a list. I took these courses, I know Python, you don't have to do it. But if you don't have any programming experience, I want you to not be completely lost. So does this sound okay? Like honor system, you just tell me and I'll trust you. I pretty much gave everybody credit on having it on their notebook, and then I got your notice, Lou, and I was like, well, I already gave you credit.
Oh.
Yeah, I expected you to do it. That's why I knew you would. A lot of trust. I know you're all here with good intent. All right, so brought my laptop, made some Python code that's less fancy than that last one because that one I had all summer to do. This one I did yesterday, or these three I did yesterday. So let's talk a little bit about what we're doing. So we're solving this problem. So far, we really haven't assumed anything about f except what?
Continuous.
It's continuous, right? So, yeah, exactly. So we've assumed continuity. We haven't assumed differentiability yet. We're going to do that in a bit, and then we're going to take it away and see how we could take it away. This is absolutely essential because I might have a sign change on an interval. I might, this function right here could look like this, just a step function. And notice that f of a is positive and f of b is negative, but there's no root in there. So that's why the continuity assumption was made. I've actually had a couple of folks, like quite a few, come up to me with concern about this class. And it's totally cool. So if you have come to me, it's more than one, it's more than two, for sure. I'm with you. We're gonna get through this. I fully expect everyone will get an A. I'm really happy to do that. If you don't turn in shit, you're not gonna get an A probably. But if you just ride along and do the work, we'll make sure you got it. I'm never gonna expect you to do something that there's no prereq for in this class. And sometimes the calculus, I know, can look a little edgy, but that's okay. I want you to see all sorts of stuff, and we're gonna integrate lots of mathematics. Whether it feels like it's integrating or not, it's doing something in your mind, tying things together. So we talked about last week, our first method was this bisection method. And I'm not sure we got past that, did we? I think that was it. So we had the bisection method. And the basic idea was we took our interval where we know our solution. So we have this bracket. We know our true solution is somewhere inside there. And we cut the interval in half, look to see which side the function changes from positive to negative. So let me put a little thing here, something like that. Looks like it's on this side, so I pick this bracket. So now I've got this half, and then I cut that in half, look for the sign change, that's my new bracket, and I play this game left and right, back and forth, until I narrow in on that root where the sign change is truly occurring, the closest, smallest interval where I can still see a sign change. This doesn't know anything about f. So notice this method really has no idea about f except, oh, it's positive, negative, but it doesn't know how positive and how negative it is. So we're going to talk about another method today that incorporates that and see if it works better than the bisection method. So two methods today. The first one is akin to this, but it's better. So an improved bisection method. This is a game in numerical methods. You look at some method and you say, how can we make this better? What assumptions with the minimal assumptions, how can we make this better? So improve the bisection method with a method that is called regula, let's see, I got some Latin, if I can spell it right, regula falsi. Is that, how do you say that, Latin folks? I know there's at least like 10 of you Latin folks in this class. Is this, how do you say that? Regula falsi? Do I have to call Dr. Oliver? How would I say it?
Lou is getting a minor.
I know, and I'm waiting for him to say something, but he's not saying anything, he's just looking at me.
I think it's regula falsi.
Okay, does that sound right?
I'd say, I don't know, it's a dead language, we don't speak
Dr.
it.
Call me a All right, so this is the fancy name. This is the more common name, the method of false position. Which is weird. I never quite understood the false part, but we roll with it because this is the name we've been given through history. Just find a slightly improved pen, better. So here's the game. We actually are going to look at f itself, not just sign changes. So we're going to look at the actual values. So step one is find an initial bracket. So that we still have to, we always have to initialize these methods unless we have some super searching that, like some sort of meta searching that picks our bracket for us. But we're going to assume that we have an initial bracket where the root is. And let's say that bracket is AB. So I've got AB here. And inside here, somewhere, let's draw a function. So make the function kind of cut across. We want the root in the right half just a little bit. And then let's make that function go really steep down below B. So this is the point A, f of A. This is the point B, f of B. And this is our root. We'll call it x star. And we can see from the picture that f of x star is equal to 0. And we want to get in on that. We're going to narrow in. I'll give you a second to finish up. Have a sip of tea. So we just talked about the bisection method, which is pretty dumb, but effective. You know, it'll get there. You keep cutting stuff in half, it's going to get small enough to get your thing there. But what we're going to do now is approximate the function f with a line. So we're going to make a linear approximation of f. And let me get a line here with red. So I'm going to draw a line between the current left point and the current right point. That's not a great line, but imagine it's a line. It's a little janky. So this is a line between these 2 points, A f of A and B f of B. Could you do me a favor and get the equation of that line? I'd appreciate it. See, just some basic math. Not that hard, but what's the equation of that line in this form? So equation of line is, I would like it in this form, y equals blah, right over here. Fill in the blank. Take a second, please. And if you get that, set y equal to 0 and find the x. Oh, you're great, thanks. Find the x-intercept of that line once you find its equation. I'll step in a minute to help with this. Make sure we got sanity. We're on the right path. And let me move this because it's probably a little hard to see. Then we're going to call this intersection C. So find that equation, then find the exact coordinates of C. once we have this, we actually have the method. If you're not sure where to start, I would use point or slope, point slope form, you know? So m equals the slope, and x naught, y naught is any point on the line. If you haven't headed down this route, maybe you're getting there by some other route, but this is most direct. And does anybody think they have the equation currently? Thomas, do you think you got it?
It's not simplified, but
Cool, can you just walk me through it? Let's do it a little bit together. Are you cool with that?
sure, yeah.
Okay, thank you, thank you. So what did you get for the slope?
I got f of b minus f of a over b minus a.
Beautiful. Could have gone the other direction, you know, with the A's and B's flipped, as long as it's consistent, good to go. Yes, sir, and then, so what point did you use?
I just used x naught equals a, and then y naught is f of a.
Beautiful, thanks. And you can also use B and F of B, and this will all work out the same, which seems a little interesting, a little odd, but maybe give it a shot, you know? When you're in these early days of math, it's good to play and just see things, see the beauty. So our equation of our line is going to be y equals f of b minus f of a over b minus a, quantity x minus a plus f of a. Awesome. Thank you, Thomas. That's perfect. Has anyone found C? Ooh. Ava, did you say yes? Oh, is that Labine? Oh, okay. I should have known. I should have known. Why? I almost didn't hear it. Labine, my friend.
Y is gonna be 0.
Okay, cool. Let me clear out my very tiny board. Okay, so to find C, we're going to set y equal to 0. I'm with you. So let's see. So we got 0. Very good. Cool. And then what did you already do all the solving? Because we could skip ahead and see what you got.
Well, I kind of had the opposite, like,
Oh.
he did f of a and I did f of b, so.
Oh, okay, cool.
Yeah.
Just for consistent, I'm gonna go with this, just so that I don't have to go back to
Next would be f negative f of a
Equals-
multiplied by b minus a.
Yeah, so I'm just gonna, times, yeah.
Yeah.
So we could just multiply by the reciprocal of that. So subtract that over, multiply by that reciprocal. This is what you were saying?
Yeah.
Yeah,
Plus
Cool.
a.
and then plus a, yeah, exactly, so that's x. Beautiful. Let's make it prettier, because it's actually very pretty. So to do this, you need a common denominator on the left, and so I'm gonna put a over f of b minus f of a. So notice what I've got right now. This is, and this is equal to c, by the way. This is our intersection point. So we've got minus f of a times b minus a plus, I'm going to multiply that times f of b minus f of a. I'm going to put that all over f of b minus f of a. And that's our intersection. And the top is super beautiful. What is the top? Look at the top. Take a second and just have the cool unfolding moment of the trick. What does the top? Does anything cancel on top?
It's AF of A.
AF of A is going to cancel on top. Notice here I've got, let's kind of do another step. So it's negative f of A times B plus f of A times A plus AF of B minus AF of A. Now you can see that these are going to cancel. If going down the route Labina did, you probably got an extra f of B up here that canceled, I would think.
Yeah.
And then that's over f of b minus f of a. And this is c, so let's just write the final simplified form. Up here, our c is equal to a f of b minus b f of a over b minus a. How pretty is that? F of b minus f of a, excuse me. Sound good? Just check it out. Make sure you're with me. And if not, if you have any questions, let me know. We'll talk it through. And that's it. Then what we do is, so let's go back to our picture. We had A, B, F looking something like this. And I took this red pen. Better, happier with that line. So, what we're going to do is mark off C, and we're now going to check the value of F at A, C, and B. So step 2 is find, actually step 2 is find C. I guess that's what we just did. Step 3 is test where there is a sign, test for a sign change, because that's the side your root will be on. So in other words, i.e. on is f of a times f of c negative, or is f of c times f of b negative. Now check that out and make sure you see why I'm using that condition. We used it a little bit last time. But it's a way to just compactly say, hey, are these opposite sign? Because that's the only way that can happen. Then if you're a CS person, you know you can have conditional and case statements. You want to avoid that. Is this positive and this negative, or is this negative and this positive? Just ugly, just very ugly. So this is a very compact, clean way to test for opposite sign. Whichever of those two is the sign change, bracket. Step 4 is reset the bracket to subinterval with sign change, where there's a sign change. Repeat, go back. So then go to 2 until your bracket is less than your tolerance in width. Bracket width less than tolerance. That's it. That's our algorithm. Pseudocode-ish. It's very pseudo code. That's our algorithm. And once you get a chance, get that all written down, let's get our laptops out and play with some code. And I don't necessarily have to put it up if we all get it out. Then that would be good. The thing that I'd like you to open, it's in the content area under root finding, is a file called bisection and regula falsi. Falsi dot Jupyter notebook is that IP, I don't know, what is it? Doesn't matter, just open that file. I always forget the extension for the notebooks. Maybe I should open this up, maybe I'll bring this up. Is everybody good on the board? Can I pull the screen down? Anybody still need it? Okay, cool, thank you. What a rig, man. This place, like this is so tall. It doesn't, it's just weird. Just weird. So I apologize in the back if you're having trouble seeing. I don't think I can even, oh, let's see, let's put some stuff under there and jack it up a bit. I guess I can use my eraser. Just remember that I put my eraser under here when I can't find it in like 10 minutes. That's a little better. Okay. Hey, holy smokes, that worked. And freaking tastic. So this is the file we should have here. I know it's tiny. I don't honestly know what to do about that. Maybe I can blow it up here a little. Yeah, I guess I can. So how's that looking in the back? Eh? Let me come see. Yeah. This is the bad line at the eye doctor.
Yeah.
Oh man, this is the one where you're
But
like
I have it
faking
pulled
it.
up, so
You're like, it's probably a C,
Okay.
I don't know. You have your copy in front of you, and
Yeah,
you
I
have
got
the vague
this.
sense of where we're looking. So look down there for detail. Okay, so this is a much terser file than I've actually done in the past. We're actually not even using NumPy in this. So I'm bringing in this package of Python functions called math, primarily to do some root stuff a little later on. But this package has everything we need. We don't really need anything fancy for this method. Look at the definition here. Here is the method, the function we're going to call. And I want to talk about this for the non-Python experienced people. So this is a function that I'm creating. It's called false position method. It takes these inputs. And when you go through the Python tutorial, you'll eventually get to this. But it takes an input A and input B. Those are going to be my left and right endpoints. It has a tolerance for how small good enough is. And then I set a max iteration so we don't run forever in the event that this thing ends up looping forever and ever. So check it out. First thing I do before I even try anything is there even a sign change on this interval? So I've got a test. Is f of a times f of b greater than or equal to 0? If it's equal to 0, that means our root's probably at one of these endpoints and I've already got it. So what am I doing this for? Because I just found the root. And it spits out, it just ends the function. It says raise value error, barfs out of the function. Then we go into a loop. And this is a for loop, a very classic style loop. When you see for, it just means this variable I will take on each value in this range. So when I use this thing that says range, it's a function that creates a list of numbers. And it starts at 0, and it runs up to 1 less than the number of iterations. So for this one, it's range 0 to 999. There's still 1,000 things in there, but just keep in mind that your final thing in this is 1 less than the number you pass in. This colon is super important. It tells Python, this is what I want you to do. What follows after this colon is the thing I want you to repeat over and over again. Notice also that there's indent. This is a tab. This is how Python knows what's inside of what. If you don't have these spaces right, Python will barf and tell you it doesn't understand what you're saying. So indentation is super important for keeping things organized. If you've been to my office, you know I'm not an organized human being. If you've been here for 5 minutes, you might know that. But I like to have my code look pretty. It's nice to have pretty. I can do a couple things organized. I can do math and I can do programming. I could not do programming well enough to satisfy the IBM folk. My code was pretty bad because I just got shit working and I didn't care how it looked because I was so desperate and stressed out. But I had time this weekend and this is fun. So we're gonna run through. The first thing we're gonna do is have everything barf because my laptop went into saver. Just like every once in a while, discount it like give it away. Yeah, I'll bring one of those little birds that dips next week. First thing we do is crank out the C, that false position, just using exactly the formula we derived. We're gonna test, is that actually the root? So it's right here I say, is the magnitude of F at that intersection of the line, is that less than our tolerance? If so, quit, and we found it. That's our root. What a coincidence, that's awesome. If it's not, so this return means leave this method and spit these values out. So it's kind of like a function. These are the output of the function right here. Update the interval. So we test for where the sign change occurs. If it occurs between A and C, then my new left endpoint will be B. Or it's the cut. Oh shit, let me just draw the picture here. So here's my line. Here's C, here's A, here's B. If f of A times f of C, in other words, there's a sign change here, as you can see, there pretty much is, because I'm right underneath there, then I'm going to let B equal C. So that means I'm just going to take this right endpoint and make that my new right endpoint. So the second round is going to look like this. I'm going to have AB where that line intersected, and then old B is out here. If it's actually a sign change on the other side, we're going to make C the new left endpoint, and so it would just shift to the right. And we just keep doing this forever. This thing is testing each time we go through, it's testing the new false position. So every time we shrink this interval, we're going to create a new false position. Let's say it's like that. It just keeps shrinking down. Eventually, this line will come close enough to our root to call it our root. And then that's when this will bomb out. It'll either bomb out then, or we'll have gone up past 100 iterations. So let's run this. Notice I'm also finding the cube root of f2, and we've been sticking with that. So my function is x cubed minus 2, and we assume that's set equal to 0. So this is my function that I'm messing with. And when I find that root, I'll have the cube root of 2. So to play this, I just literally click in that box, hit play, and oh god, I thought I got an error. I didn't. That's yay. So look at what I've done here. I've actually also incorporated the bisection method below. So I've also got the bisection method in here so we can compare. Notice that the false position method got this approximation for the cube root of 2. Pretty much the same thing for the old bisection method, but look at the number of iterations required. So it took 26 with bisection, it took 21 with false position. Because we're adding information into the system, we should expect things to be a little more efficient. So it converged faster. This doesn't seem like much, but crank up the magnitude or crank down the magnitude of the tolerance and we will see a bigger difference. So let's go into that piece of code. and mess with the tolerance. I want to actually talk about that in just a second. So I'm going to make it 1e to the negative 12, and then hit run again. You don't have to save or anything. You just make that change. Oh, yeah, change it in both of these functions. So there's 1e negative 8 in false position and also in bisection. Change those both so that we have the same tolerance. Then hit play. And it runs so dang fast. But now we're seeing almost like a 25% improvement in how many iterations this thing takes. So now there's a difference of 8. The more refined this gets, the more the distance is going to show. And it kind of depends on the function as well. But we just improved our first numerical method with just a little bit of geometric insight. I'm working on an assignment for you. The assignment's going to be using some of this code to explore some problems. So the assignment isn't going to be from scratch, write me some Python that does this thing you've never heard of. The assignment's going to be, you know all that Python code I wrote and put up there? Hack that, take that, and modify it to do what you need to do. Toward the end of the semester, I'll definitely be having you do more, but not yet. Is there any questions on this, friends? Yeah? Good. Okay, cool, awesome. So, let's go to something. I'm so freaking excited about this because I made something really cool this weekend. And I'm very freaking stoked about it. But let's get there. I'm so stoked about AI too. I cannot wait until ChatGPT can see from my phone. It's coming. It was supposed to be out. I paid for the membership earlier in the summer because they made it seem like it was coming soon, but it was a fake out. And it had Scarlett Johansson's voice at that point, and that was pretty cool. I really enjoyed that. But then they took it away. So I can't wait for my robot friends, because I do love the robot people. Oh, here it is, isn't it? I'm not worried about the takeover by robots, right? Like I'm just gonna immediately try to suck up to them and do what they need me to do. I don't know, harvesting people or whatever I got to do for them. Harvesting silicon from people's fillings or something, you know, I don't know. Sorry. I'm reading some horror right now. It's got me thinking about that. So let's talk about our next method, and a much heavier assumption is made here. Let's assume that f of x is differentiable. Near our root. And we're going to exploit that differentiability. You don't want to make an assumption and make a narrower class of functions and then not use that information. As soon as I know a function is differentiable, remember that means it's smooth and it doesn't do that. So let's just make a little note here. So here's f, here's x. This is a non-differentiable point because it's sharp. And let's talk about what that sharpness actually says geometrically. So a function is differentiable if it's smooth and it doesn't have a crease, doesn't have a bend like this or a cusp. Cusps are like this. They almost kind of get very sharp. This one's more like an absolute value function or something. So why is that bad? Because we're going to use tangent lines to get more information, to get to our roots. And if I go to a smooth spot, there's only one tangent line through any particular point. So at a smooth point, and it's weird to talk about a point being smooth, but we just mean, is it smooth near that point in a sufficiently small neighborhood? At a smooth point, the tangent line is uniquely defined. There's only one of them, and we can find it using good old definition of slope, and in other words, this, the f prime of x is equal to limit of f of x plus h minus f of x over h as h goes to 0. That is, this limit will exist there, and it will give us the slope, tangent slope at x. This point is wickedly bad, because think about a sharp thing. So here's a sharpness. I want a tangent to this sharp peak. Well, there's infinitely many. It could just rock back and forth and teeter on there. So it's not uniquely defined at a sharp point. So here, tangent is not unique. Tangent line is not unique. So differentiability gives us a unique tangent. That's one good way to think about this. All right, so now we are going to derive what's called, before this class it was just called the Newton's method, and I'll probably refer to it as that, but it's actually also called more, just like Newton just consumed so many things, that if someone was doing something like what he was doing up in his ivory tower with his riches, just doing nothing but science and math, the Newton-Raphson method is the same thing, but it gives credit to somebody besides freaking Newton. I mean, come on, bro. Do you not have enough? And Newton also kind of still, he didn't do all that from scratch. He built upon the shoulders of giants and had a good publicist. So, Newton's method. So what we're going to do is start again. I've got my function f on a bracket. So again, I need an initial bracket. Where I think my root lives, pretty certain of that. And let's say that we've got a fairly lovely curve, and let's make him kind of curve up a little bit like that. So that's f, and it's all smooth from the way I've drawn it. I'm indicating smoothness there. So this is f of a, this is f of b, and this is smooth. And there's our root. There's our buddy that we're trying to find. So what we do is make an initial guess inside that bracket. You always want this bracket just to know, okay, any value in here is going to be a good starting point. So step 2 is choose an initial approximation in the bracket. And we're going to call that x sub 0. So I come to my x sub 0 right over here, and I say, okay, that's kind of close. It's pretty far off when we look at it, but it's better than over here, right? So it's something. So x sub 0 is approximately the x star, depending on how big your error tolerance can be. So we're going to go up to the function, and we're going to turn it into a line again. But this time, I'm not going to just draw the line between the two endpoints. I'm going to find the tangent line and follow it down to get my next approximation, x sub 1. So let me write that up. You've probably seen this before, right? You've seen this at some point, Calc 1. It's one of the applications. So step 3 here is find the equation of the tangent line at x naught, f of x naught, and calculate its x-intercept. So we're basically saying, let's use linear approximation for our function, treat that like the function. Where does that have a root? And calculate its x-intercept. We'll call that x sub 1. Our next approximation. And we're just going to kind of repeat this over and over and over again. using the new approximation as the current one, and then using that tangent line there to find the next level. So let's do this. Could you do me a favor, friends, and find the equation of this tangent line here at x naught? What's the equation of that line? So this has got to shake some Calc 1 neurons alive. What is our slope going to be so that we're all on the right page? What's our slope?
It's that one limit you wrote earlier.
It is, yes ma'am, it's the derivative, yeah. So that's right, Josephine, yeah, it's the slope is equal to the value of the derivative at their current point. So in other words, here it's going to be f prime of x naught, which we know exists because we assumed it would exist. So we can find that. So that's your slope. You have one point you have to use. It's this point right here. I'm leaving off one little bit of information, but you can find it. And if you get that, then determine where it intersects 0, or where it intersects the x-axis. So once you get that equation, again, figure out what is x1 in terms of x naught. That's our goal. And if you need any help, just let me know. Happy to help. Oh my. Cool. What's the point we're going to use? Yeah, heard that. So I said, Labina, I can't
No,
even
that's
help.
not.
Got
Yeah, I
it.
said X naught.
Oh,
It's so quiet.
Not you two.
Oh.
Not you two. You got it. Okay. So Ava, what was that? X naught what?
X naught f of X naught.
Thank you. Yes. So let's get that point slope format again. Crank it out. So y equals f prime of x naught times x minus x naught plus f of x naught. Find the x that solves this. No. Solve. Very similar moves to the last thing we did. Really, really similar. That's why it's kind of a cool next topic. So I'll just go ahead and slowly work through this. Right, so get him over. Let me know if I did that right. I think I did. So I'll just make sure we can get there, that we understand how we got here. Yeah, cool. There is a move I made that may or may not be legit. I did something dangerous, super dangerous in computer world. what did I do that I need to like at least make some assumptions about?
Is it like you're not sure if the slope at that point 0?
Exactly, yeah. So I divide, thank you, yes. So right here, when I divided by this slope, I was assuming it was non-zero. So in Computerville, that might be close to 0, and when I divide by it, I might introduce huge amounts of error. So if I take a really small computer number, you know, like 10 to the negative 10th, and I reciprocate that, it turns into a really big computer number that may or may not have all the pertinent details maintained because of the conversion to IEEE 754. So this is a dangerous move, but we're going to do it anyway. So let's make a little note. Note, if f prime of x naught equals 0, we have trouble. Let's look at a picture really quick as to what is happening. So let's take a look right here. I've got a function, and let's say goes like that. Make this bump down and then a bump up, so I want a local min and a local max. If this is my root, this is the thing I'm trying to find, x star, and I pick this as my initial x, where does the tangent line take me? To infinity. It never intersects. So notice that if I'm at a local max, a local min, a local max, or even just a place where it gets kind of flat, like an x cubed graph. This is negative, here's an x cubed. That gets super flat right at the origin. So any place where I have a horizontal tangent is going to be bad news for Newton's method. So this horizontal tangent won't intersect x-axis. So that's a thing we need to keep an eye on in these implementations. All right, so this is just the thing we're going to repeat over and over again. This is an iterative scheme. Is there any questions getting there before I kind of make it more general? So think about how this is going to work. I'm going to do this again. I'm going to say now, oh, here's my new approximation, x1. I'm going to feed that into this formula to get x2. So in other words, x2 is just that value that came out minus f at x1 over f prime at x1. And if I continue that down, I can just generalize this scheme. The next approximation, sub n plus 1, is the current approximation minus this ratio. And we loop n equals 0, 1, 2, until tolerance is reached. That's it. That's Newton's method. Super nice. Let's see, are there any other things to talk about here? No, I think we just need to play with it now. So it's a really beautiful equation. The only downside, and you're going to see this in the code, is that I actually have to have a formula not only for f, but I need a formula for its derivative. So I have to code that in directly. I have to literally give the formula for f and its derivative, so I have to know some Calc 1. And you will have to know some Calc 1, or at least a place where you can type it in and Calc 1 will be done for you, which is how life works. So that's all good. Okay, so next module I'd love for you to open up, my friends, is the one called Newton's method. That's super precarious, but way better. Nice. So again, looking for that cube root of 2, defining my function as the cube x cubed minus 2, but then I have to enter its derivative. Keep in mind, exponentiation is 2 multiplies. It's star star. So that's x squared right there, 3x squared. And then here I've got the method. Let's go through it. I'm passing in some parameters, and I want to comment on these last two because I forgot to do it on the last time. Anything that's not specified, like these two, is required. So I need to have f defined. I need to have the derivative of f defined, and I need to have an initial value chosen. If I don't specify this or this, these are the default values. So for example, if I said, call Newton's method, I can't block that, but call Newton's method, and I just specify these 3 and put a little right paren, it'll be okay. It will accept that, and it'll know, oh, the tolerance is by default this, and this is the default max iterations. So these are optional parameters. If you pass them in, you can change them to something better. So we initialize, we've got this variable x that's going to keep track of our current approximation. Again, we run through the range of max iterations, and if f is not small enough, if the derivative of f is big enough, look here, this is the derivative at our point. I want to make sure we're not getting near 0 with that derivative so that I don't shoot away to infinity. So I'm making sure that's not going to happen, and then I just go through and define x nu according to the formula we just derived. If the, check this out, this is a little bit different than what we've been doing. If the new approximation minus the old approximation in absolute value are less than our tolerance, we'll stop. We return, we spit out that new x value, and then this is the number of iterations we've done. Otherwise, the current x value equals the one we just got, and we start over again. Sound okay?
I have a
Yep.
question.
Yes, ma'am.
How good does the initial guess have to be? Like, does it have to be really close, or can it be like super way off, and then we'll just correct for it?
That's a great question, and it's going to be probably a homework question at some point. No, but it's a great one. Let's play here.
Okay.
We can play with this and mess around with it. I think this is a great place to do it. But one thing you'd have to worry about, Ava, is are there maybe roots that are near this one that I might pick up accidentally? You know, so there's lots of weird things that could happen. But that here I don't think we're going to have that because everything here is real valued, so we're all good. So just go on in here, click in there, highlight it, hit play. And that actually took a little bit of time. Look at the pretty things I've made here for you. So, let me scroll up. Example 1 was solving this. Initial guess was 1. And here's our actual root. We found that pretty good with 6 iterations. 6 iterations with a tolerance that was somewhere between the two we originally did. So this would take 20 iterations of bisection method or regular falsy. This is really fast. Thank you. I gotta just kind of do the settings. So now let's go down to the second example that ran. And let's look in the code first. So I've got multiple things kind of crammed in here, unfortunately. So go to example 2, just scrolling in the code. One of the things that can happen is really cool. You can get caught in infinite loops because what happens is that the tangent line takes you back to a place that's going to take you back to the place the tangent line came from. So you end up bouncing between these two. So this is a classic example. X cubed minus 2x plus 2. There's its derivative. Actually, that comment is completely false. I need to X that comment out. So we guess x equals 1, And look at what happens in the graph as we run through this. This is just all the same Newton's method, but look at the picture below. Here I'm printing iterates. So this is, the first iterate is 1. That was my initial guess. Then it bounces to 0. Then it bounces back to 1, 0, 1, 0. It's in an infinite loop. And it will never leave that cycle. So one thing you could do in this code is test for cycling. If it starts bouncing back and forth a few times, you're probably stuck. So you could test for that and leave. And then finally, I put in one method down here where it barfs according to the way we talked about, where a horizontal tangent occurs. So we got to go into the code. And here I'm using x to the 1/3. X to the 1/3 looks like this. This one's actually kind of barfing. What's the slope of the tangent right there? X to the 1/3. What's the derivative of x to the 1/3? Our rule?
1/3 minus 2/3.
Yes, absolutely. So this is actually 1/3 x to the 2/3. Notice that at 0 it barfs. So your derivative, your tangent line is completely vertical, so it's got an infinite slope. So that's just kind of a cheesy example of how things can go really bad. Yeah, this is a nice little function you might need from time to time. Cube root, nicely built into NumPy. Cool. So I want to talk more about this example, and we're going to have some fun. I got 15 freaking minutes left. This is great. Everything we will do in this class is real numbers. I will never ask you to go into the complex realm. There's some of you who've already been there with me. We've been to complex magical lands, and we had a great time. I'm going to turn this off for a second so I can explain what's about to happen. So let's look at my eraser right there. Let's see if we could do Newton's method in the complex realm. And the answer is you just do it exactly the same way. It's kind of amazing that it works out. But let's talk about cube roots of 2 for a second. So if I asked you to solve this equation, x cubed equals 2, find the cube root of 2, you would, well, gosh, I hope you've heard it enough that it's the cube root of 2, that you've been, here long enough to know that this is a real solution. Are there other solutions? How many other solutions?
2.
2 others. They're in the complex plane. So the complex plane has a real axis and an imaginary axis. And in here, we create what are called complex numbers. This is a plus bi, and I is this most primal imaginary number. It's the square root of -1. Doesn't make sense in our heads, but makes sense everywhere else. It basically makes physics and go round. This is real stuff in a very real way. The term imaginary was so badly chosen. But back then, people were really scared of numbers. Like, people didn't have much to be scared about, I guess, besides like the plague and shit. And living to 25 or whatever it was, But the mathematicians had, they had great lives. They were taken care of. They worked for kings and just did math for a king. What a great gig, right? So every time a new number came along, someone had a heart attack and thought the devil made it, right? So 0. Oh my God, 0. What is nothing? Stop talking about that. That's upsetting. Okay, we won't talk about it anymore. Negative numbers, be gone, beast. And then irrational numbers. That was a big one. That was a big heart attack for the Greeks. Pythagoras found this, and they just could not wrap their heads around the irrationality of 2. And then came along I. And for a while they did some work with it, and then they forgot about it because they were like, this is just silliness. Let's not go on. Well, it turned out to be very real. So you can actually make a picture of a real number plus some multiple of I. This is called a complex number. That's my sign for number. And you can indicate it in a plane. The x-axis is the real portion. The y-axis represents the imaginary portion. So if I said 2 minus I, that would be 2 units over and 1 unit down. That's right here. You can think of this as kind of the point 2, -1. It just syncs up with the plane in the same way. So if I told you, what does this look like in the plane? You'd say, it's just that point, it's no big deal. Except you can combine these things in interesting ways. So for example, if I take I and I square it, what do I get? -1. I get a negative number. So I can do things like take 1 plus I and square it. And one thing you will use for the rest of your scientific life is FOIL. FOIL is gold. FOIL. We hail FOIL. So I'm going to FOIL this thing out. 1, that's first. Outer is I. Inner is I. Last is I squared. That's -1. So this is 2I. So I can do math like that. And as long as you understand roughly what just happened, you're in good shape. So if I take I plus 1, or 1 plus I, and I square it, I actually get 2I right here. If you were in complex analysis with me, you know that we just kind of rotated. We took the angle here and multiplied it by 2, and then squared the length of this line, which is actually square root of 2. Now it's 2. So anyway, there's all sorts of cool stuff we can talk about. But all you need to understand for this is that this whole plane is filled with numbers. And once I talk about the cube root of 2, so when I talk about this equation, cube root of 2, what is it? It's like 1 point, what were we getting? 1 point what? No, that's the square root. 1 point what?
2599.
Thank you. 2.6-ish, right? So that's approximately the cube root of 2. Turns out there's 2 others and they're hidden up in this imaginary stuff. They're equally spaced around the plane. So if there's 3 roots and they're equally spaced, there's 120 degrees between them. So I'm going to take this, I'm going to rotate 120 degrees. I'm over here, so there's 120. I've got this root here, and then I've got this root here, another 120. I'm keeping this length the same, so I'm literally just taking this segment, even though it's not done well. I'm just taking this length and rotating it and finding where I go to. So over here, this would be one of the imaginary cube roots of 2, and there's another one. Imaginary root, here and there. I don't quite know what they are off the top of my head. I'd have to do a little trig, and it's going to look ugly, but we can find them. So we can do this Newton's method in the complex plane, and here's how it's going to work. We're going to start with the complex plane. You're going to see a really pretty picture too in just a second. We're going to start with the complex plane. We're going to use this iteration scheme that x next equals x old minus our function at x old divided by f prime at x old. We're going to use the same damn scheme. And the way to get into the complex realms is you pick an initially complex number. So what I'm about to show you is an implementation of Newton's method with a very cool twist. We're going to, so we know there's these 3 roots hidden in here. We're going to assign a color to each one. So I'm going to say one's red, one's green, one's black. So I'm going to say, okay, this one's black, this one is green, he's already green, cool, and then this one's red. And I'm gonna turn the plane into a grid that I'm gonna sample from, and I'm gonna kind of just run through every point in the plane, as many as I can. I can't run through all of them. So I pick a point, and I'm gonna call that x0, and I'm gonna do this. And I'm gonna watch where it goes. So it's going to do some weird stuff. It's gonna move around a little bit, but what I'm gonna see is that it'll start narrowing in on one of these roots. And so this one went to the green, so I'm gonna color the initial point green. And I'm gonna do this with every point in the plane. So if I went to another one that's right next to this, and use that as x0, and it bounces around, blah, 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 and I see it getting close to this, I'm gonna color it red. And then I'm gonna do the same thing for the green points. I'm gonna do that to every point in the plane. Assign them a color by where Newton's method sends them for roots. Let's see what happens. Literally one of my favorite math things. I've got so many favorite math things, but this is top of the list. So there's another file that says complex Newton's method. Would you please download that? Complex Newton's example. And I'm just going to let you run that. So we're still, again, looking for the cube root of 2. But hit play. And we'll give it a second, because this actually takes a while. This is cool. Your computer's really actually doing something. I'll pull down the screen, too. That looks pretty shitty. And I don't think I used red, blue, and green. I'll show you. I actually set some weird colors. I've got orange, blue, and light green, but you can tweak these. For fuck's sake, man. Just stop. Bro, thank you. Dude. So if you want to rerun this on your own, this is the RGB levels of the point, the colors. You can just set different mix levels here and get different colors out. Again, I'm putting this up so you can have this stuff to play with when you get assignments. Anything cool happen? Scroll down. Looks pretty cool. Looks pretty freaking cool. Thanks. That's all I needed. I just needed some affirmation. Thank you. Thank you, Courtney. But it takes a while, especially depending on what your laptop is like. Ah, there it is. Look at that. So this is actually a little bit ass backwards in a way. Oh no, this is right. So this is a basin of attraction. That's the technical term for this. This is a fractal. If we were to zoom in on this, we would never see an end to the detail. It continually reemerges, this beautiful braid over and over again. So if I start near cube root of 2 over here, all this stuff goes to the cube root of 2. That's the color for cube root of 2. But other stuff way over here goes to cube root of 2, the positive version. This green area is for that imaginary root, and this blue area is for that imaginary root. In other words, if you start near them, you'll end up at them. But there's many places where you will also end up at, and they are woven in this unbelievably intricate way. So, freaking awesome. Now watch. Let's tweak this just a minute. I'm going to do the fifth roots of 2. So I come up here, I just tweak this function, make that z to the 5th. I have to tweak the derivative. So it's 5z to the 4th. And I'm going to run it again. I should have 5 roots now. So in the plane, I should see 5 roots spread around with those beautiful braids. I should have could tweak the text or made the text customized. Oh, look at that. There they are, there's the fifth roots. And so this is the real fifth root, and then these are all imaginary fifth roots. Now let's see one last thing. Let's take a journey. A journey together, my friends. Oh my God, I'm afraid. I'm about to open up YouTube. I don't know what's gonna be up here. I hope it's not weird. I'm definitely not opening up an existing video. God knows. I mean, I'm not like a total like creep or anything, but you know, it's my private life. It's a lot of crypto crap and like looking up Elden Ring stuff. So let's see here, some newtons. Oh, I might not be hooked up to the Regis Wi-Fi. Let's try that. Yep. You're gonna make me. Do you usually have to sign in, or is it just?
No, you can.
It's okay, awesome. And DeFi King, okay, the Grateful Dead and DeFi Kingdoms, okay, whatever. Okay, cool. That's all good. Oh, and then the guy I can't stand, and I hope he goes down in flames. Okay, so newtons. What's that? Yeah, I love Pac-Man. Yeah. Newton's method, root, zoom. Let's try this one. I'm sure.
The algorithm begins with a random guess. Let's call it X naught.
Okay. Oh my gosh.
Since that would require
Here we go.
points on the boundary between two regions. You try boundary.
This guy's explaining the stuff that I just explained. And he's not just, dude, I love this guy, but he's a little verbose right now. Here, that looks, you see that shape there? That's totally there we go. And leave it to the Germans. So these are the fifth roots of 1. Usually like to put on Pink Floyd for this kind of stuff. It's pretty good. Journey did the Heart of the Sun. That's a great one. And eventually, so they're just zooming, they're blowing it up, and they're just changing the point about which they blow up. And so these are zooms over and over again. Eventually you'll reach the computational limits of the machine, and you'll see it start to fragment, because of precision. But they probably have a very high precision machine, maybe like quad. There you go, see? Hit the precision limit. Das ist fucking timer or whatever that's over there. Yeah. So, take a look at this shirt really quick. I just wanted you to see this because we're gonna talk about this. I thought we'd get there today, and I try not to wear t-shirts more than once because of stink. Yeah. I'm sure you're used to it from science faculty maybe, but this picture right here, take a look at it. Remember, this is a shirt I made out of it, but okay, cool. See you all on Wednesday. I'm gonna try to have an assignment for you this week. That's my goal. And we'll wrap this up then.
Thank you, friends.
Do you want me to turn this off?